So today we're going to talk about significance testing. And the logic behind significance testing is to decide between two competing claims and to see how likely it would be to get a sample statistic this or more extreme given that the null hypothesis is true. So the null hypothesis is a statement we're trying to find evidence against. It's also known as a statement of no difference. And the alternative hypothesis is the statement we're trying to find evidence for. Now notice the language of these definitions. We are trying to find evidence for the alternative hypothesis and trying to find evidence against the null hypothesis. We're not trying to prove one of them true, we're just trying to find convincing evidence. When we're writing hypotheses, we always use the parameter. We never use the statistic. So two-sided versus one-sided tests is what we're going to talk about right now. And two-sided tests are when the null hypothesis is stated parameter equals value and the alternative hypothesis is parameter does not equal value or parameter is different than value. And this means that essentially the parameter could be either larger or smaller than the hypothesized values, so you would have to see the probability of both of those cases happening. And a one-sided test is when the null hypothesis is parameter equals value and the alternative hypothesis is parameter is greater than value or parameter is less than value. And so it essentially changes the way that you would calculate the probabilities. And so calculator versus no calculator is an essential piece to this because two-sided versus one-sided tests are really important in two areas. They're important in the way you state your hypothesis, and they're important in how you solve for the p-value. So here's table A, and the table entry for z is the area under the standard normal curve to the left of z. And if it's a one-sided test, that's fine, that's what you want. But if it's a two-sided test, you would have to multiply your probability by 2. But if you're doing it on a calculator, you won't actually have to do anything to the p-value, but you'll just go to stat, and then go to tests, and I'll just put on one prop z test. And then here it says proportion is not equal to hypothesized value. Proportion is less than hypothesized value, or it's greater than hypothesized value. It would account for the differences between one-sided or two-sided tests.
So the first type of error we're going to review is called type 1 error. And type 1 error is the probability that the test will reject the null hypothesis when the null hypothesis is actually true. So if you have the sampling distribution for p hat, and if the null hypothesis of 0.08 is true, then the probability of rejecting the null hypothesis is the area that's this blue shaded region. So what this shows is that the probability of getting a type 1 error, which is rejecting the null hypothesis when you really shouldn't, is equal to the alpha level, because the alpha level is the probability that you do reject the null hypothesis. The second type of error is called type 2 error, and this is when you fail to reject the null hypothesis when the alternative hypothesis is actually true. So if the null hypothesis was that the population proportion was 0.08, and the alternative hypothesis is that the population proportion is greater than 0.08, a type 2 error would be if the true proportion was 0.09 and we fail to reject the null hypothesis. The power of a test against a specific alternative is the probability that the test will reject the null hypothesis at a chosen significance level, which is alpha, when the specified alternate value of the parameter is true. And we graph a normal curve, assuming that the population proportion is equal to a null hypothesis. The alpha value shows how likely we are to reject the null hypothesis. However, if you graph a normal curve, assuming that the alternative hypothesis is true, this area under the graph shows the power. And it is important to remember
power and type 2 errors are complements, and power can be increased by increasing sample size, effect size, and alpha level.
I'm going to talk about confidence intervals and how we can use them to draw inferences on two-sided tests. The most important thing we need to always remember is it in the interval? So if P is the proportion of females in an AP Calculus class, and our null hypothesis is that the proportion of females is 0.5, and we are trying to see if it is not 0.5, whether it's more or less. Now, if we're given a confidence interval at 0.48 to 0.51, then 0.5 is included in this interval. So we fail to reject because we can't be sure. Even if it is 0.51, we aren't sure because 0.5 is in the interval. Whereas if they gave us this confidence interval, 0.51 to 0.54, we can reject our null hypothesis because 0.5 is not in the interval. These were at a 95% confidence, and we are trying to conclude on an alpha at 0.05 level. Do you see how these are, the 0.05 and the 95% are related? Or we could, if we had a 90% confidence interval, we could only draw conclusions at an alpha at 0.1 level.
Basically, the p-value is the probability of obtaining your sample mean of proportion or a more extreme one if you were to repeat the same significance test with another random sample of the same size. Remember to assume that the null hypothesis is true, and then state the probability of getting an observation as a more extreme in another random sample using the p-value, so your p-value is going to be that probability, and then state whether there is or isn't convincing evidence for the alternative hypothesis. The most important thing to remember to earn full credit is to state each hypothesis in context. So for this example, the null hypothesis in context would be the mean number of students per class CCA is 40 students, and then this would be the alternative. Always remember to interpret type 1 and type 2 errors in the context of the problem. So as we see here, we have the null and alternative hypothesis. A helpful tip to remember the difference between the two errors is that fail to goes with type 2. A type 1 error would occur if convincing evidence that the true mean number of students per class at CCA is greater than 40 when the true mean number of students per class at CCA is indeed just 40. And so when we're interpreting the consequences, describe the major risks that the errors have beyond the study, such as factors that affect the consumer or the factors that affect the company. Lastly, to interpret power, state the condition of the true proportion or mean value that is given to you in the FRQ or question, and give that power as the probability of the test giving a value less than or greater than the null hypothesis. It's basically the probability of getting it right.